Hey, I'm Karthik, and today we're solving maximum sum of edge values in a graph. I hope I can explain it in a way that saves you time and saves you the agonizing pain of actually going through and figuring out the mathematical nuances of solving a problem like this. It isn't exceptionally hard to understand. It just involves maybe a bit of luck and uh, some good attention and some good brain power. Anyways, you are given an undirected connected graph. So we know that the graph is connected. This is a really important part of the problem. I thought we were working with unconnected graphs for a bit. And anyways, we're given n nodes, number from 0 to n minus 1. Each node is connected to at most two other nodes. This is another crucial part of the problem. Basically, each line over here is important and you need to keep everything in mind while solving this problem. I know people who jump right into the input output uh, before starting to solve their questions, but nah. Leetcode hards really involve reading and understanding the question to the best of your capability. Anyways, each node is connected to at most two other nodes. The graph consists of m edges, represented by a 2D array edges, and an edge indicates that a particular an entry into this edge vector indicates that there is an edge between the nodes A and B. So what we need to do is assign a unique value to each node such that the value of an edge, which is the product of values assigned to the nodes that it connects, is a maximum score, right? So what that means is, in normal English, given four nodes, the numbering of the nodes actually does not matter. You can just imagine the 0, 1, 2, 3 were not there. We need to assign numbers to them or special values from 1 to n, that is 1 to 4. After assigning the values to these nodes, we need to compute a score which is given by the sum of edges, where the edge score is calculated by the product of the values we assign to the nodes that that edge actually connects. So, for example, in this question, after assigning these numbers, we have a final maximum score of 23, which was obtained by multiplying 3 into 1, 4 into 3, 2 into 4. And that gives you output 23, and that is the maximum in this case. So we know for a fact that, one second, we know for a fact that each node can only be connected to at most two other nodes. So we could have a particular case like this. We could have a particular case of some kind of cycle like this, but we could not have another node over here. That would make this invalid. So uh, essentially, we have two main patterns that we identify. One is that of a chain, and one is that of a cycle. So let's take that's our first major observation actually. That we could either have chains or we could have cycles. So let's take the case of chains first, right? So assume we have like a 5 node chain, classic pentagram. Do you call these pentagrams? I don't even know. Whatever. Let's say you have this particular 5 node graph, and we know we're working with connected graphs, so all nodes are definitely connected. We need to number this graph. So we could probably number it in a fashion like this, say 1, 2, 3, 4, 5, and we need to compute the score. Now, obviously, just by intuition, I guess, we know that this would not give us the best score because we ideally want to multiply the bigger numbers with other possible bigger numbers to achieve a higher product at the end of the summation process, right? So the fact that we think in this way, in this greedy manner, means that we need to use some kind of greedy approach to the problem. We need to ensure in a greedy fashion that each number is multiplied with the maximum possible numbers so that the resulting product is the largest. So let me quickly erase these. So if we were to give this node the value of 5, we know that we would ideally give its connected nodes the values of 4 and 3. Okay. Then we would give 4, the next highest node, the next possible highest value, which is 2. And 3 would get the remaining node value of 1. In this case, we've achieved the maximum possible product. So the answer would be 5 into 4 plus 4 into 2 plus 2 into 1 plus 1 into 3 plus 3 into 5, whatever that equals, right? So we have used a greedy approach in this manner. Now let's look at the case of cycles. Sorry, let's look at the case of chains now. My bad, guys. We were looking at cycles now. Let's look at the case of chains. Let's take the same 5 node situation, right? We have a chain of nodes. The only thing that differing between the chain approach and the cycle approach is that the chain approach has a missing edge, which would have gone ideally, which would have ideally been the least weighted edge, right? Uh, Again, let's number this, right? We could number it uh, in a fashion such as 1, 2, 3, 4, 5. But we know again that this is not the most optimal because why is 3 being multiplied with 2 and 4 when 3 could also have been multiplied with 5 instead of 2? So we know that's not the optimal case. So we can view this chain solution as an extension, or rather, maybe not an extension, but rather a subtraction from the cycle problem. So let's assume that it was a cycle instead. And now let's number the nodes, all right? Let's say if we number the nodes 5, 4, 3, 2, and 1. And all we're doing here is we're solving the same cycle problem, but we're going to remove the least weighted uh, edge. So now we have a 5 node cycle that is optimally numbered. So let's look at this cycle approach once again. There is an interesting mathematical property over here that all odd nodes, in fact, stick to one side, whereas all even nodes appear to be on the other side of the graph. That is a mathematical approach that will really help us later on in the problem, because now we have a algorithmic way of assigning our values to the nodes. Okay, so we have a brief understanding of how we can assign the nodes, as well as how we can um, divide the entire problem into 2 subproblems of solving it either for a chain or a cycle. So so now that we have that rough overview, let's actually look at the steps we need to take to solve the problem, right? So the first step, of course, is determine if it is a chain or a cycle, because then 2 processes would then follow. If it is a chain, or let's start with cycle actually. If it is a cycle, we need to do the following, right? We need to label the nodes and well, start with the highest possible value, and then from there, through some kind of mathematical subtraction, work our way down to label the other nodes of the graph. And if it was a chain, we would follow the same process. We would just not have the final step that takes place that would link the least weighted edges. So yeah, that's roughly the best way I could explain that. I'll work on my explanation prowess, but hopefully, looking at the code, you guys can understand that a bit better. So here we have our uh, problem statement, or the function given to us by the problem itself, which is for us to return the max score, right? Just to be clear again, the max score is returned by the sum of edges, where edge values are a product of the labeled nodes that of the 2 nodes that the edge connects, right? So we start by creating an adjacency list. Okay. Now over here in this edges array that is provided, all we have is uh, the distinct number of edges as well as what a pair of nodes they connect. But here I'm creating a proper well-defined adjacency list uh, with the first node and its corresponding connected nodes, as well as doing it the other way as well. Because yeah, that's how we do adjacency lists, so that every node and its adjacent nodes are documented. So now we define a visited vector, which I have created as a Boolean type. This is to ensure that we visit each node exactly once, and this will help us in determining whether our given graph is a cycle or not. And this is a pretty simple DFS algorithm that I think we learned in our algorithms class to determine, and in fact, probably the main one of the main important uses of DFS was to determine whether a particular graph has a cycle, if I remember correctly from the slides. Anyways, uh, this is to determine if the given graph that we are passing here to the adjacency and visited vectors has a cycle or is a cycle or not. So once we determine whether the particular graph is a cycle or not, here we enter the main algorithmic part of our code. Uh, just to uh, just to quickly run over the DFS algorithm, I won't spend much time here. Once we enter a node, we up the count of total number of nodes present in this cycle or present in this chain, and we mark the visited vector to indicate that we have visited this node. We iterate through all nodes that are adjacent to this particular node. If the node is a parent value that is being passed, we skip it. If we have already visited a node that is present in the adjacency list, we know that it has a cycle. Else, we run DFS on all the other adjacent nodes, and we know hash cycle is a Boolean value, which is why I'm using the OR property, because if any particular visited node in the future is determined to be contributing to the cyclic nature of the graph, we want this entire hash cycle uh, boolean to reflect as true. So we need an OR basically to determine if any other edge or at least one edge is uh, present in the cycle or not. Sorry, at least one node is contributing to the cycle or right. Determining if the graph is a cycle is what this function does. And now, once we have determined that the graph is a cycle, we now need to determine the score. Okay, let's run through this, right? Let's use this example actually. Oops. Uh, I wonder if that'll paste. Never mind. I will just draw it out, right? We have 6 nodes here. Cool. So the most optimal way, of course, as we decided, uh, was to start by numbering and then going and attaching the highest remaining possible values in a greedy manner to its neighbors, right? So let's say this particular node has a number 6, right? We don't have to, in fact, store the values that we are assigning to the nodes. All we have to do is compute the score as we go through it algorithmically, right? So right now, once we know that once we assign the highest possible value to a node, the n minus 1 and n minus 2 are the nodes that will be connected to this highest possible node. So that's exactly what's happening here. So as soon as if the cycle is determined, we know the cycle length is the total number of nodes in the cycle. In this case, cycle length is 6. Uh, we update the score value. So essentially, right now, the score is given by n into n minus 1 and n minus 2. And then we reduce the total number of nodes and the cycle length that needs to be computed. Because right now we have dealt with these 3 nodes, we can assume them to be complete. We can decrement n by 3 and cycle length by 3. Uh, so as long as the cycle length is greater than 0, we need to assign the values of the next few nodes. So right now, n's value has reduced from 6 to 3, right? So where should 3 be assigned? we know 3 should be assigned to the next highest value node possible, which is 6. Essentially, 3 should now be multiplied with 5 to instead of 4, because this gives us the maximum value. And this is conveniently n into n plus 2. If you remember, all odd nodes would come on one side, and all even nodes would eventually feature on the other side. So what we have here is a situation where we're just using the property that n into n plus 2, when n is 3, it will have to be multiplied with the next odd number node. Then we decrement n and the cycle length by 1 to indicate that this particular node has been processed. We move to node 2. 2 will be multiplied by 4, 2 into n plus 2. We process this node, reduce the cycle length, and we come to node number 1, right? Uh, Now node number 1 will be connected to node number 3 in this similar way. 1 into 1 plus 2 is 3, and that will handle these edges of the graph. These edges of the graph are now processed. I'll reduce this to make it a bit more readable. So now we have successfully processed these edges of the graph. However, the minimum weight edge is still remaining and is still left to be processed. And we can simply, as right now, n would be, after finishing this, the n's value would eventually reach 0. So what we can do is simply add n plus 1 and n plus two's product to the final score. So this is the perfect case of a cycle, and I think this is relatively simple to understand. Now, once we have the basics down, I think this is relatively simple to understand. Now to determine if the graph is a chain, a cycle would be false. Now, what we do is we handle a few set of base case conditions. Of course, a cycle could have just one node in it. In that case, there would be no edges, and we simply return 0. If the chain has a length of 2, right, we simply multiply n's value also would be 2 given in the question. We would simply multiply 2 into 1, which is n into n minus 1, and return the score. In fact, this computation is unnecessary. Uh, Now, if we have a chain of length 3 or more, right? Now we have the problem of assigning weights. Over here, since we only had two nodes, assigning the weights was arbitrary. You could have assigned a higher valued weight either here or here. It wouldn't have made a difference. But now we have to actually worry about assigning the nodes. So we can follow the same process as we did with the chain. If you remember, the same process as we did with the cycle, because the chain process is the same as the cycle process, except that we will ignore the minimum weighted edge at the end, which we computed here. So as you can see, it is the same process. The only thing that is missing is the computation of the minimum weighted edge, and that returns the final score. Oh, that was an absolute pain to explain, and I heard that was a terrible explanation. But I hope in some way you guys could understand that. And yeah, I'm going to work on my explanations. I really have work to do. Fine. Anyways, see you guys. Bye bye.